Assalamualaikum and good day. We continue back our discussion in microprocessor 1 course, second part of the course which we going to discuss about 8086. In the previous uh, discussion, we look into an advancement in microprocessor from the early stage until nowadays. So today uh, in this discussion, we are going to look into a detailed architecture of the 8086. Okay, so in 8086, or we can call it 8088. Also, it is the same architecture, only some features of it different. Okay, when we talk about increasing speed of the microprocessor, actually there are two ways in increase the performance of the microprocessor. If you look nowadays, each year the manufacturer can outcome a better performance than previous one. So how they make it better? Okay, there are two ways. Okay, the first one is increase the working frequency. When you talk about increase the working frequency, you refer to the using the physical technology available, which will need to think of the cost consideration. For example, you make other kind of, for example, increase the number of transistors in certain area, means that you can reduce the size. Then you can claim that there is an improvement, as we know that uh, the transfer of the electron from one space, one location to the other location. If the location is less, mean that the transfer is much faster. Or uh, the other way to make the performance improve is by changing the internal architecture of the CPU. So this is the one that uh, changing from the previous one, 8085 to 8086. That have done. Okay, if you look in here, this is the internal block diagram of 8088 or 8086. It is much more easier to say 8086 because after that they have 8286, 8386, 8486. Okay, if you look here, there are uh, two structure. We call it as EU and BIU. Okay, we are going to look into detail later on. Okay, this is the architecture of the 8086. So what made it improve from the previous one, 8085? Because in 8085 could fetch or execute instruction at any time given. Okay, one activity can be done. Okay, either you can fetch or you can execute. So the improvement made to 8085 is the idea of pipeline. Okay, in the simplest form is to allow the CPU to do the fetching and execution at the same time. Okay, if you have the pipeline is the one that improvement made from the 8085. Okay, make the system, the information being processed much faster. Okay, if you look, there are two in the figure. There are two architecture. The one without the pipeline, and the other one is with pipeline. Okay, if you look here, the one without the pipeline, call it fetch. Sorry, it need at the one time it can only fetch, and the other time to be execute the one that being fetched, and then fetch the other instruction and then execute. While the difference between the improvement that we made to 8086, okay, in the beginning you fetch at t plus 0 and then t plus 1. The next time it can execute the first one, while execution it can fetch the second instruction. Okay, this is at the same time being done. Okay, at the third time, t plus 2, if you look, it can already execute the second instruction. If you compare with the non-pipeline, it only can fetch the second instruction, while with the pipeline, it's already execute the second instruction, and so on. So this is the improvement that we made to 8086. Okay. Inside the 8086 pipeline, Intel implemented pipeline in 8086 by splitting the internal structure into two sections. That is the given figure previously. I've been mentioned execution unit, EU, we call it EU, and bus interface unit, BIU, where these two sections, EU and BIU, are actually working simultaneously at the same time, both of it. Okay, where if you look back, the EU is the one that we've all registered, and the BIU is the one that queue up the instruction. Okay, BIU access memory and peripheral, while EU execute instruction previously being fetched. Okay, this work only if the BIU keeps ahead of EU. So the BIU of the 8086 has a buffer or queue. Okay, in the beginning, at the first time 8086 be introduced, okay, it has 6 bytes of queue. Okay, it can queue up 6 bytes. While in 8088 it is 4 bytes. So this is the difference between 8086 and 8088. But the architecture is that remain the same. Okay. Uh, so 8086 pipeline has two stages, fetch and execute. Where it more powerful computer, it can have many stages. So in the later 286, 386, 486, okay, and then we have Pentium and Core. Okay, they have more pipeline. Okay, maybe certain K pipeline. So you can imagine it become more faster to execute. Okay, okay, if you look, if any instruction which takes too long to execute, the queue is filled to capacity and the buses will still idle. Okay, that is the lag, the uh, but there is a way. There was a way in order to overcome this all. Okay, the buses which sit ideal. Okay, later on, we can study it out. Where in any circumstances, the microprocessor must flush out the queue. Why? You have already queued up all the instructions. Suddenly, you need to flush. Okay, that is you, you are going to experience it once you understand how to uh, design the program, okay? Especially if you can avoid a jump instruction. Okay, if you have a jump instruction executed, the BIU start to fetch information from a new location in the memory. It's not in the sequence. Okay, suddenly it goes to the other location. So means that the one that it being executed, it being fetched to put in the queue need to be flushed, need to be empty and uh, go to the new location. So in this sense, it means that it was the same as the previous architecture, like 8085. Means that you have the capability in order to do the pipeline, to execute and fetch at the same time, but suddenly it make no useful because of this instruction. So there was a way in order to avoid it or try to make it less use the jump instruction. Okay, the EU must wait until the BIU fetch the new instruction. Okay, if you jump, then you need to fetch the new instruction in the new location. Okay, and this we call it in the computer science terminology is a branch penalty. We should avoid it as much as possible. In a pipeline CPU, too much jumping around reduces the efficiency of a program. If you have a lot of jumping instruction, you jump to a new location, you need to flush. Actually, you reduce the performance of the architecture being available. Okay, now we look at the register inside the 8086. Actually, if you are studying more advanced, uh, there are a few thousand register inside the 8086. But the one that can be accessed by the program is the one that we within our scope. Okay, we are going to study it. Okay, in CPU, in 8086, okay, register store information temporary. Okay, register we consider as also a memory, a really fast to access memory. Consider, okay, it can be either 1 or 2 bytes of data that we process. Okay, the address of the data. Okay, so this is the information that can be stored. Okay, 1 or 2 bytes of data that being to be processed or the address of that data. Okay, a general purpose register in 8086 processor can be accessed as either 16-bit or 8-bit register. Okay, either way you can use it, either 16-bit or 8-bit register. Okay, all other register, this is general purpose register. General purpose is the one that we call scratch pad. You can use it to manipulate, to add, to multiply, to that kind of register. while all other register can be accessed only as a full 16-bit. Okay, there are other kind of information register which can only access can be accessed 16-bit, only 16-bit, cannot access with 8-bit. Okay, okay. As you know that in 8086, data types are either 8 or 16 bits. So in case that you want to access 12-bit data, for example, a 16-bit register, then you must use the highest 4-bit and you set it to 0. So only 12-bit that have a value. For highest bit, you need to set it to 0. Okay, the bit of a register are numbered in descending order. Okay, in descending order. So you start with from the left D7 until D0, D6, D5, and so on. And in 16-bit D15, D14 until D0, where the first letter of each register indicate its use. Okay, in uh, okay, this is the general purpose register. AX, okay, is used as the accumulator, and BX is used as a base addressing register. Okay, later on we are going to look how it been arranged in the instruction. And then we have CX. Okay, CX is used as a counter in the loop operations. And then we have DX, which points to a data in the IO operation. Okay, okay, these are in the table show all the register that used in the 8086. Okay, first category we have a general register, which we have AX. It is a 16-bit. If you want to use AX for 8-bit register, then you can have AH and AL. Okay, for 16-bit register, you use AX. While if you want to use the register in 8-bit, then you can use as AH and AL. Okay, same goes to AX, CX, and DX. Okay, all of it can be used either in 16-bit or 8-bit. Okay, same as AHAL. For register BX also, you can have BH and BL. And also for CH, CL, DH, DL. And then you can have a pointer register, which is, as I mentioned, other than general register, all of it are 16-bit. So for pointer register SP, which point to stack pointer, and then you can have BP, where the register is a base pointer. And then we can have index register, also 16-bit. SI is a source index, while DI is a destination index. And then we can have a segment register, also 16-bit. We have CS code segment, DS data segment, SS stack segment, ES extra segment. Okay, then we have instruction category instruction. It is a instruction pointer. IP, it is a 16-bit. And then we have a flag register, FR, also 16-bit. Okay, so for you to remember that only general category register that can use as 16-bit or 8-bit, while the other register, pointer, index, segment, instruction, and flag only 16-bit. Okay, now we go, once I have the idea that register that can be used in the 8086, we can start to uh, go for assembly language, programming in assembly language. Okay, CPU can work only in binary, which consider very high speed, and you know it is tedious and slow for human to deal with 0 and 1. If you let's say if you want to generate instruction in 0 and 1, it is difficult. It's really tedious. That we call it as a machine language. And this machine language actually the one with 0 and 1, or you can write in hex. During my time, my undergraduate study, actually I'm writing code need to write in machine language, not assembly language. We don't yet have an assembly language. We only have the what we call the table to look up, okay, and it convert from binary to hex. But you need to key in the code in hex, mean in machine language. We call it as a machine language. But okay, a program of 0 and 1 is called a machine language. Early computer program actually code program in machine language. You need to write 0 and 1, or you can convert it into hex. Eventually, assembly language were developed which provide more mnemonic for machine code. Okay, mnemonic is typically used in computer science and engineering literature to refer to codes and abbreviation that are relatively easy to remember. Okay, easy to remember. Assembly language is referred to a low-level language, same as the machine language, which it deals directly with the internal structure of the CPU. Okay, that is the difference between engineer and computer science. Okay, computer science, they don't, they are prefer to use the high level language. Okay, they don't bother about the architecture of particular processor. But for engineer, actually, you need to know, it is better to understand the assembly language, to study and to know, since you know the architecture of the particular processor. And you have to bear in mind that assembly language is different between the processor. Okay, it's not the same. For 8086, it's not the same as 8085. Or in Motorola also, 68,000 for example, or in Zilog Z80, and so on. Okay, to program in assembly language, programmer must know the number of register and their size. Okay, that is why the low-level language, if you are going to use it, then you need to know the number of register and their size, as well as other details of the CPU, means the architecture of the CPU. Okay, today there are many different programming languages such as C++, Basic, C Sharp, and so on. Okay, this kind of language is called a high-level language because the programmer does not have to be concerned about the internal CPU details. And high-level language are translated into machine code by a program called a compiler. You know, every once you want to use the processor, everything need to be converted into a machine language. Okay. To write a program in C, one must use a compiler to translate the program into machine language. Okay, once you write in higher level language, then you are going to compile it to generate a machine language. An assembly language program consists of a series of lines of the assembly language instruction, where an assembly language consists of a mnemonic, which optionally followed by one or two operands, where the operands are the data item being manipulated. If you want to manipulate, you want to add, you want to multiply, divide. Okay, this is what we call operand, the data. While the mnemonic are the command of the CPU. Okay, if you want to add, you write add, means add is a mnemonic. Okay, what do those telling it what to do with those operand, those items. Okay, two widely used instructions are move and add. Okay, this is one the examples. Okay, the move instruction copies data from one location to another location. Okay, we look at the format. Okay, we have MOV. Okay, this is the mnemonic, and then we have the operand, the first one, destination, and then the source one. Okay, after the second operand, then you put semicolon. Okay, whatever right after the semicolon is considered as a label only. It's not going to convert into a machine language. Okay, this is a label for you to understand what you are doing for the instruction. Okay, so in this instruction tells the CPU to move. In reality, copy. It means that you copy. You didn't modify the source. Okay, the source operand to a destination operand. You only copy from the source. Okay, if you put here BX, this is AX. So take the value inside the register BX and put inside the AX. Okay, for example, okay, in this instruction, move CX DX mean copy the contents of register CX to register DX. Only copy. Okay. After the instruction is executed, register DX will have the same value as register CX. So means CX will remain unchanged. Okay, this program first load. Okay, this is one example. Program first load CL with a value 55 hex. Okay, if you put what we call it, the character after the number means that it is what kind of base that being used. H means hex. Then move this value around to the various register inside the CPU. Okay. If you look here, 55 is the data, the value. You put 55 into the CL. Okay. Put, move If you look after the semicolon, this label is not going to be translate compiled to machine code. ACL just for your information, and then move DL CL means CL copy to DL, then DL CL will contain 55, and so on. Okay, AH DL. You have to bear in mind that here you are using the 8-bit register. So that's why the number here is 8-bit. A55 is 8-bit. Okay, here is the use of 16-bit register. Okay, 46 8F hex. Okay, you move this number into the CX, where now CH, okay, CH means the higher 8-bit is contained 46, and CL is the lower 8-bit contain 8F in hex. And also same for the other. The only thing is, as I mentioned, other than general purpose register, there are only 16-bit register. Okay, it didn't have a low, or it cannot be accessed by 8-bit. DI, SI, DS, BP, okay, index register, segment register, pointer register, okay, all are 16-bit. So in 8086 CPU, data can be moved among all the registers, where as long as the source and the destination register match in size, except the flag register. Okay, why? Later on. Because flag register, you cannot change it. Okay. Here you look at, there is no such instruction as move FRAX. You cannot move whatever content in X to FR. Okay, since the flag is the bit in the flag will reflect after each instruction be executed. It will change. It kind of indicator. You cannot change. You can observe it. Okay, the use of flag register is to observe. Okay, code such as move ALDX will also cause an error. Why? Because DX is a 16-bit register while AL is a 8-bit register. So it will pop up a syntax error. Okay. One cannot move the content of 16-bit register into an 8-bit register. Okay. It's not allowed. Okay. If you look here, DX is a 16-bit, AL is the 8-bit register. So it's not allowed. Okay. And then using the move instruction, data can move directly into a non-segment register only. A non-segment register only. The following demonstrate legal and illegal instruction. Why? Okay, this is a 16-bit data move to AX is illegal. 16-bit data move to DX. General purpose register is legal. Also legal. If you look here, this is DS is a segment. Okay, DS is a segment register is considered illegal. It's not allowed. Okay. CX is okay. You want to move 16 bit. CS is a segment register. It's not allowed. Okay, it is illegal. Okay, BH is a 8-bit register of BX. Okay, it is legal. Okay, value cannot be loaded directly. The number, the data, you cannot, the value you cannot directly load to see the any segment register. CS, code segment, data segment, extra segment, and SS. To add, if you want to put a value, you need to load it to load a value into a segment register, load it to a non-segment register. Okay, what is a non-segment register? AX, DX, all the non-segment register. Okay, you load it first there, and then you can move to the segment register. So only between register to register, if you are going to load into a segment register. Okay, this is an example. You move a value to AX, then from AX you can load to the DX. This is legal. This is allowed. Okay, okay, you can move to DI. Okay, it is not segment register, and from DI you can load to the segment register ES. Yeah, this is allowed. If a value less than FF X less than F is moved into a 16-bit register, the rest of the bit are assumed to be zero. Okay. For example, if you move BX with 5, if you didn't 5, okay, the result will be 0, 0, 0, 5. The rest of it is 0. So BH will be, the higher 8-bit will be 0, and the lower 8-bit will be 5. Okay, the other thing is, if you write the value without any character after it, so it consider decimal number. If you write it after it is H, it is a hex number, 16 base. And if you put B, it means a binary number. It is base 2. Okay, moving a value that is too large into a register will cause an error. Okay. You have a 8-bit register BL, you want to move 7, 5, F2, okay, is larger than 8-bit, so it's legal. Okay, if you look here, this is the first instruction should be less than 8-bit, 8-bit and less. Okay, the value is greater than 8-bit. While the second instruction is greater than 16-bit. Okay, so it's considered illegal. Okay. Okay, that is about move instruction. Now we look at the add instruction. Okay, this is the format of add instruction. Okay, you have add destination source. Okay, add the source operand to the destination, where the source operand will remain unchanged. Add tells the CPU to add the source and destination operands and put the results in the destination. To add two numbers such as 25 and 34H, Each can be moved to a register, then add together. What you can do is you put a 25 first in AL and then put the second number 34 hex in BL, and then you can add together, where the result will be in the AL, okay, the first operand, where the BL will remain unchanged. So after you execute the instruction, AL will contain 59, okay, 25 add by 34, 59 hex, where BL will remain unchanged, 34. The contents of BL will do not change. Okay, the program above can be written in many ways depending on the register used, such as, okay, these are the options that you can use. If you use DHCL also, uh, I mean, it's possible to be used and it is correct. Okay, where after execute the last instruction, CL will remain unchanged 34, while DH is 59. Okay, it is necessary to move both data items into register before adding them together. No, it's not necessary. You can have also other option. For example, here you have you use the same register DH, you load with 25, and then you execute the second one where you add DH with the second value. The result will also be the same as previous instruction. The only thing is that you only use only one 8-bit register. Okay. In case above, while one register contains one value and the second value followed by the instruction as an operand, the second operand is a value, immediate value. Okay, this what we call the call an immediate operand. Okay, the 8-bit register can hold numbers up to FF hex. Or if you are going to use a number which is larger than FF hex or 255 in decimal, then you can use a 16-bit register such as AX, BX, CX, or DX. Okay, the following program which can add, okay, this number, these two number, which these two number is bigger than FF, is bigger than 8-bit. So what you can use, you move the first number into AX, the second number, and then you can add it. Okay. This is an example to show that if you are going to use the uh, bigger than 8-bit value. Okay, we stop here.